Добрый вечер.
Добрый вечер.
Добрый вечер.
Добрый вечер.
Добрый день.
О, добрый день, да.
Артем, вы как будто на какой-то фабрике находитесь.
Так и есть на заводе по имени Яндекс.
Мгм. Понятно.
Так, куда же докладчик пропал?
А он был?
Нет, я не знаю сейчас, был он или нет. Я
Ну,
только
наверное.
что дошел, и я его не вижу.
А кто докладчик?
Я вроде здесь.
Сейчас Иван должен делать доклад.
Слышно, нет?
Вот, все видно. И видно, и слышно, все.
Хорошо, сейчас включусь. Ссылки. Одну минуту.
I think we should switch to English. I see that Peter is here at least.
Yeah.
And
I would probably understand it.
no, let's not. It's easier for us to speak in English, I guess. No, because you know, if you speak, you know what you are saying. And if you want to understand, you don't know what, so it's more difficult. So, but actually, there is, maybe you can comment something about the history. Probably you are the only one who can remember something about the history of this question, both about universality and about asynchronous automata. Maybe you can just say a few words, what is the state of art, or how it appeared, and what was the story, and so on.
By you mean whom?
You, Peter.
Oh, I never, I don't think I ever kind of studied this question seriously, right? It somehow, okay, so I worked, of course, in this reliable cellular automata, and it was but that was a synchronous model, right? Everybody, each cell moved at the same time. And then, so somewhere probably in the end of 80s or so, I met once Joe Miller, and he brought up that, well, actually you can make a synchronous cellular automata, you can simulate it asynchronously if you introduce this simple modulo 3 clock. And okay, so that was there was no question actually. I don't remember any question to anything to solve. But then later, or somehow at the same time, then actually, yeah, somewhat independently, who is it?
So let me check that I understand correctly. So
Yeah.
the synchronous automaton is an obvious thing. Finite
Yeah.
states, finite set of rules, and transitions at the same time.
Yeah.
And asynchronous, we also have the finite state of the same transition rule, but we can apply it at each moment of time. We apply only to some cells.
Yeah,
And there are some.
yes, I mean, there is of course, there, if you understand it precisely, it's less simple because, yeah, and of course, if it is just a finite automaton, you can say that you just pick a random cell and let it move, and then pick another one and let it move, and so on. But it kind of in the infinite case, what does it mean exactly to continuous time Markov process, right? And with infinite memory cells, it's actually not so simple. But the Americans already studied this, and that's the model they use. They called it interacting particle system. And the general case is actually to show the existence of such a model. Actually, it's not that simple. If you look at the, so there is a book by Liggett with this title. And if you look at like his first chapter or two, you will see that it's actually a complicated mathematical construction. Uses some difficult theorems, and you can then create some special cases, right? When each cell just uses a Poisson process to independently of the others to update itself, right? But kind of the general case is more complex. But I mean, it's probably all this is not too relevant to the question of universality and so on. So, so anyway, then there was a paper. So in connection with this computing cellular automata, then there was a paper by Simon and Berman still in the 80s, right? I think, who also gave a nice, a nicely understandable proof for the Thom theorem, but also gave a somewhat similar construction for simulating an arbitrary cellular automaton asynchronously. And actually, they proved that if you do this, in the continuous time model, then the delay caused by this synchronization, I mean, the average delay caused by this synchronization is only a constant factor. So, right, so, and it's actually a nice, simple, but still somewhat clever proof. And so I didn't do much with this, but the next time I started to work on cellular automaton, when I wanted to give a continuous time version of my one-dimensional cellular automaton, then at that point, essentially I just used this modulo 3 trick or modulo something trick, but I posed myself this question at the time. Okay, really, what is the general question of kind of simulating a synchronous computation asynchronously, and wrote this little paper about that. And then I tried to publish it, but somehow then at that point, this journal, Information and Computation, somehow, I don't know, they never produced me a review, and after a while I just gave up. And it didn't look like, it didn't look like its theorems were very original. They may actually have some of its main theorem probably is in other versions, in other disciplines already existed. So I didn't insist on that. So I just put it on the archive and that's it. But it's kind of the problem of the problem of having a asynchronous version of Cellular Automata is still, I think, a very interesting one, but it's more a probability theory problem because the simplest, in my mind, by far the simplest example of a reliable computer is our construction with John Rife of a three-dimensional cellular automaton that simulates a one-dimensional one reliably. But that's hopelessly hopelessly synchronous. It's very important that it goes in lockstep. And then we were thinking about, okay, how if you apply this modulo trick to it, then the new problem arises. Okay, then whether the errors introduce deadlocks or too long delays into this version. And that is still, it looked like the deadlock problem in a way was solved by Cook and Winfrey, but it is still dependent on somehow not having very long probabilistic delays, and that problem is still kind of open. But then I think all this has nothing to do with just the question of simulating, of universality in the asynchronous case. So I guess, as I
Okay,
say,
let's then proceed and see what is happening, and then maybe you will comment after the talk.
yeah. So
also
I mean, this is essentially
what you think about
or,
it.
I mean, for me, as far as my interaction with this issue, this is all I had to say anyway.
Okay.
Okay.
Yeah.
So I think they started drilling a bit, but hopefully it goes away. So there won't be any background noise. Otherwise, yeah, I'm ready to start with the presentation. And, yeah, it's an honor to have Peter Gash here, given that I used a lot of concepts from his original arXiv paper that got mentioned beforehand.
Well, he already knows how we admire him, so no need to say anything.
Okay. So
Yeah.
So yeah, let's start with the talk. So today
Yeah,
we're
we
gonna
see
talk
your
about-
slides. Yeah.
Perfect. So today we're going to talk about asynchronous cellular automata, many topics, some older, some newer ones. So as a refresher for the people who don't know what cellular automata are, forgot. Cellular automata are these simple one-dimensional systems where the evolution happens locally. So, some of you probably know the examples of Game of Life or, Langton's loops, where you're using, a large array of cells where each cell behaves in the same way. You can achieve complex evolution patterns. So more formally, how does this work? So we have an infinite d-dimensional array, so in this case, one-dimensional, and then every cell applies the same local rule at the same time. So we're in the synchronous case at the moment. And, already with two states, black and white or 0 and 1, and by applying XOR rule, we can achieve pretty interesting patterns. So if we start with a single black cell and apply the cellular automata rule, which is described here, we will get the Sierpinski triangle. And the computation is very simple. You just compute the XOR from yourself and your left neighbor. This pattern, which shows the time evolution of a single row over time, is known as the space-time diagram. And usually all the interesting things happen in a space-time diagram and not the single row, because it's easier to interpret.
Yeah, it was a Pascal triangle modulo 2, also known as.
Yeah, exactly. So some formalisms, because this time we'll have some more formulas. So the cellular automata is usually defined by a quadruple, where we have a set of states, a neighborhood, a local room function, and the dimensionality of our array. And the synchronous application of all local rule functions across the whole array is known as the global rule function. So that's why the definition of a global rule function takes an infinite configuration and then updates every cell log based on the local rule function and its neighbors. Also, to refer to one-dimensional automata, we'll use Wolfram codes. They describe all binary one-dimensional automata by encoding the transition table. Yeah, exactly 8 transitions that you need to define in a single 8-bit number based on which transitions turn to 1 and which don't. So yeah, that's all pretty basic stuff, and this is all synchronous. But obviously now we move to the asynchronous case. Now in the asynchronous case, we drop the assumptions that all cells update at the same time. That means every cell can update in its own tempo, and a space-time diagram based on so at each point in time, we pick a subset of cells and update. It could be a finite subset of cells, it could be infinite, it could be all of the cells. And if we plot the asynchronous space-time, we get something more chaotic as this, as you can see on the left. So some cells updated, some cells still lag behind. However, an observer from the outside doesn't see this diagram. It sees what happens on the right, because we assume that we don't know. What cells were picked.
So let me check that I understand correctly. So we update, there is also local rule, and we may apply the local rule to some subset of cells at any moment. And still, it may include cells which are neighbors to each other. So
Yes.
It's not just we update one cell, they are dependent. So we cannot get the same thing obtaining just one by one. We can update several cells together, and this is not equivalent to sequential updates for cells.
Yes,
Yeah.
you can pick. So there's multiple definitions. We pick the most general one here. You can take any subset of cells, neighboring, not neighboring, not necessarily sequentially, and update it. So as we see, there are already multiple issues. So first of all, we don't know. We assume that we don't know which subsets were updated, which makes our life harder. And we also cannot observe it, because what if maybe a cell was updated, but it didn't change its value? How do we know? We don't. So let's define some formalisms here as well. So we define the concept of an asynchronous update schedule. And it's essentially a function which for every point in time gives us a subset of cells which was updated. And for an update schedule to be valid, we require every cell, this should be just ZD instead of S to the power of ZD, should appear infinitely often in the image of a function. So essentially, every cell is updated infinitely often, but the function has the flexibility of deciding which cells it updates at every point in time. Now, the update history is defined as the change for every cell in the time. So every time a cell changes its state, I don't know why the Wi-Fi doesn't seem to work properly for the laptop. So every time the cell changes its state, we record a change in the update history.
So the update is for a given cell, or for no? We didn't see your formal definition, but maybe you can just say it's defined for entire infinite configuration, or for each cell separately.
So each cell has its own update history. Obviously, you can look at them all together,
Mhm.
and then you have the global update history. And yeah, as soon as it reconnects, I can show the definition again. Yes, that's the idea. And the last concept on the slide, which will reappear
We still
shortly,
don't see
is-
your slide. Maybe it's even better if you explain everything without it, but we don't see it.
Yeah, I also don't see it.
Okay.
So,
Yeah, so forever is, but then somehow there should be some theorem, some definition of stability that somehow the behavior doesn't depend on the sequence of updates. That's is what we will expect. Yeah.
exactly. So what we want to have is we want to have a cellular automaton such that its update history is independent of the update schedule. So it doesn't matter in which subsets we pick, at which point in time, like this history, which describes the change of the cells, which we observe is update independent.
No, but it's not clear how it's possible. So imagine that we try to update some cells many times while others are not updated. So I guess that nothing should really happen because somehow this is just useless trying to update the cells in the same neighborhood. And
Yeah, but the definition of the update schedule,
yeah,
trying to get it back, says that every cell is updated infinitely often. So if you give me infinite time, every cell will be updated infinitely often.
yeah, you know what I am saying, that if you just define the history of update, but just exactly as a record what happened with a cell, so what rule was applied and what was the neighbor states at that moment, then if you update the same cell many times without updating the neighbors, probably in a reasonable automata nothing will happen. It will just see that information did not come and we don't change anything, I guess.
No, yeah, I guess so. It's probably so you have to assume that cellular automaton rule allows you, just to leave the state the same, right? You will not. I mean, you can consider it an update or not an update. So when maybe it's better to call it update attempts, right? So arbitrary subsets suffer update attempts, but the one possible update of the cell is just to stay the same.
No, but just one should say how we define it. Do we just omit all the update attempts which didn't change the state, or what?
The sequence. So when you look at the sequence of states, I think. Well, I have to ask Ivan whether that's what he means. But I think when you look at the sequence of states of a cell, then I suppose it will not have repetitions. But maybe I am mistaken.
Well, let's read. Finally read. So the update is the sequence of configurations, and configurations of the entire automaton.
Yes. So
not
the
of a
idea
cell.
is that we don't have repetitions. So
you see here, it shows that it doesn't have repetitions. Yeah.
No, but just
so essentially for every cell, we keep the log of its updates.
No, the update history is something for a cell, or configurations H0, H1, and so on. They are just configurations of the entire automaton, or a state of a cell. Just in this definition.
What you do is you look at the update history for every cell where it changes, and then you glue these histories together to get configurations.
You see, so the history of the cell, it only shows when the state changes.
No, I don't see. So H0, H1, and so on are configurations of the entire automaton, yeah? Or of a cell. I guess for automaton.
Sasha, this isn't true. HT of I, HT is not a configuration at any time. it consists of pieces of certain configurations, as you see from.
No, but just I cannot just let's read the definition
Leave for a
formally.
minute and read and
Ivan,
get a
Ivan,
cable.
maybe you send to someone your slides and we will share them. Somebody.
Okay, I can do that too. Or I can try to get a cable, but I think that's easier because for some reason the laptop is not working properly. I'll send them to you.
Okay.
So maybe while Ivan is sending, Kolya, if you understand what is the definition, can you just explain it to us in
I haven't
parallel?
yet got the definition, but I only.
Okay, let's then wait. Yeah, no problem.
Uh-huh.
So you can try to share them opening. If you open some windows, I get you can share them.
Sorry?
No, it's I just saying Kolya that if he got the file, he should open in a separate window and then.
I haven't got the file yet.
Yeah, it's still sending.
Still sending, yeah. Okay,
It doesn't take long.
let's. Ah, no, there is a
Yeah,
complicated file
sorry.
because there are nice pictures which are moving, so it couldn't be short.
Yeah, it might be the reason.
Isn't it just a PDF file?
Yeah, this is a PDF file. It's just animated one. But I'm sending it. Yeah, I'm very sorry. It should not have been like this. Okay. 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 Should arrive soon. Okay.
Ага.
Ничего, получил? Did you get?
Получил сейчас.
Great. Then we can.
Okay. I sent it 3 times. One of them should work.
Все. Ага.
Just you open a separate window and share this window, I guess.
Да.
Yeah.
Так. Теперь я могу расшарить сейчас. Ничего, уже получилось.
Да. Ну хорошо. Покажи тогда тот слайд, на котором мы... Just show the slide.
Этот?
No, update history. Yeah.
So you see the update history is something, so for each, there is certain t prime. You are right.
No,
This is
H0 is a function of I. That's what I'm saying. So it's the configuration of the entire thing, yeah?
Right. This is a configuration at some time t prime, where t prime has a complicated definition.
No, so for every cell you have a different, for every cell I you have a different t prime. Because t prime is dependent on I. So it's for
so
every
t prime
cell.
is dependent on I. That changes everything. So it's not
let's read the definition. So t prime is the minimal number. And so it's just a state number I state in the history of t state in the history of a cell, yeah?
Yes.
Right.
Exactly.
Yeah, so if the state does not change, we do not care. But if the state changes, we move the local clock of a cell. And they are not synchronized, but assuming that everything goes well, which is not guaranteed, but normally each clock will move infinitely for a cell. It will somehow probably change the configuration infinitely many times. And then we just record this sequence of HI is the configuration made of ith states of every cell.
Yes.
Okay, and then last rectangle. So if the update history is invariant for any zeta, or what does it mean?
So invariant history means that on
yes, Kolya, you did something bad with the slide.
I see. Sorry.
Yeah, can you restore it somehow?
There should be like a button which clicks present or something. Or
Maybe you can present them one by one, not as a sequence of.
I know this PDF viewer, and you should probably press F5.
F5. Okay.
Let's see. Better?
Yeah, better. Yeah, great,
okay,
fantastic.
Okay, so hopefully
Хорошо иметь пророка, да. Okay.
Okay, so we have invariant histories on configuration C. If doesn't matter which update schedule we choose, we always will have the same update history. So if you see the definition in a previous of the update history, it's reliant on the update schedule.
So whatever sequence of updates we have with this very weak restriction that every point is updated infinitely many times, we have the same history in the sense that we know it's uniquely determined what will be after the 100 steps, 100 changes of states in any given cell, independently on which order it's updated. So it's quite unobvious why such an automaton exists.
I mean, it's a trivial automaton.
It's not obvious.
Yeah.
The trivial automaton has that property.
Of course, if the automaton change its states cyclically, like 0, 1, 0, 1, 0, 1, then of course it has this property. But
Okay, yeah, we will
Yeah.
discuss just that shortly.
Yeah,
So yeah,
yeah.
it's not obvious why like complicated automata with these properties exist. And actually, the point of this talk would be first to convince you it's actually very obvious that they exist, and then to convince you back it's actually not obvious at all that they exist, and it's really a coincidence that it just all works out. So it's kind of two opposite goals. But let's move to the next slide. There is a good example for
Да. Коля, move to the next slide. Yeah.
Yeah, so here you can see an async. So here you can see a trivial automaton which always flips a white cell to a black one and a black one to a white one. This is called rule 51. And as you can see, the asynchronous spacetime is very chaotic. So here I updated every cell with probability 90%, and we get a completely random looking pattern. However, the update history is invariant. And because every cell just flips from white to black, from white to black, from white to black. So the update history for this asynchronous spacetime is this nice zebra pattern. And for any other update schedule, it would be the same because this automaton has invariant histories. It always flips the cell.
Yeah, the time goes up, yeah, in these pictures.
Oh, the time goes down.
Okay, yeah, or down, yeah. The time goes
So
down.
we start with a single black cell, and yeah, we get what we get.
Yeah,
Okay.
but actually, if we have just a automata with two states with any rule, it also has the same stability property invariance, because we don't ignore the cases when the automata doesn't change the state, and if it changes the state, it will just be 0 1 0 1 0 1. So somehow it's almost, in this case, it's for two states, it's almost meaningless to speak about stability because everything is stable.
No, not completely. For example,
No?
some cellular like you can go in a black cell where you don't update anymore, no matter like what happens.
Yeah, you can still, yeah.
So you can assign, so actually even with two-state automata, maybe you can design something smart so that you kind of, get stuck in a black cell only if a certain condition is fulfilled. So maybe, yeah, it's not that trivial, but yeah, the invariant history will look almost the same, except sometimes it may freeze at for certain cells.
Yeah.
So to take away of what we've seen before, if we have invariant histories, we have usable or robust ACAs because we can look at the update history and get the information out of there. And now we have 4 questions that we want to answer. First, how can we characterize all automata with invariant histories? If we can we decide whether an automaton has invariant histories or not? Can we construct complex automata with invariant histories? This goes back to the point mentioned before. And finally, what are the limits of asynchronous computation? So now moving to the next slide, there's actually a success story for that. And because for reversible CAs, all of these questions have been answered in a very beautiful way. So we know that this is an intermezzo to see like what our ideal goal would be. So first we know that the reversibility is decidable in 1D and not in 2D. Then there is a very beautiful characterization of all reversible CAs as a composition of CAs, cellular automata which just shift and permute the blocks. Then there is also a very smart partitioning technique which lets you construct arbitrarily complex reversible CAs which simulate Turing machines and everything by partitioning and shifting the cells. And finally, there's also a nice theorem which says if you have a cellular automaton in D dimension, you can simulate it naturally with a D+1 dimensional reversible cellular automaton. So all of these it took decades to answer these questions, and all of them have relatively elegant proofs. So we would want to have something like this, but for asynchronous CAs. That's like the maximum goal.
I want to mention that at least the first results are all Yarko carries, right?
Yes, both of them are. But so the first one is by Jaakko Kari, then the second one was started by Kari, and then I think Kari proved it for 1D and 2D, and then for 3D and upwards it was proven by someone else. The third one is by Morita. So he actually came up with all sorts of partitioning techniques which are very fun looking. And the last one is also by Toffoli and Morita. But yeah, this is not so relevant for us. It's just like what we want to have.
Okay, that's another story. Probably, if we go into this detail, we should explain what is reversible and what is block and shift. But if it's not strictly needed, maybe we should move.
No.
And
it's not needed. It's just an inspiration. So now we further, and we'll talk about algebraic characterization.
But just you can say one bit. So is it possible to translate any automaton, cellular automaton, into some asynchronous version which in reasonable sense simulates it? Yes or no question. What is your
yes for most automata.
Okay.
And so now now I'm presenting the results by so we have two properties which turned out to be very useful to characterize a synchronous cellular automaton. So first we'll start with an active cell. An active cell is a cell that if you would update it right now, it would change its state. Then there's the property of monotonicity. And essentially a cellular automaton, a synchronous one, let's think synchronous for a second, is monotonic, that if you, or asynchronous, doesn't matter, that if you update, nobody of the cell's neighbor can stop it from updating. So if we have an active cell and update some of its neighbors, but not the cell itself, the cell still remains active if it would update it after that. So I'll make an example afterwards.
So let us read it. So active means that it changes if updated. And you say that if something was active, then after any updates of any other set which doesn't contain this cell, our cell again should be active.
Sasha, not other.
Exactly.
Other means I is not in A. I see.
Yeah.
Okay. And then there's a second property, which is the property of commutativity. So if you take two disjoint sets of active cells, all of them have to be active in these cells, and then you update them together, it results in the same thing as first updating one set and then the other.
No, I would say commutativity would mean that it's the same if we update B and then A, but it's even somehow you can even update all them together.
Yes. So let's move next to the next slide. So informally, monotonicity, if I can update, nobody can stop me from updating. Commutativity, however, if I can update, nobody can stop me from updating, and nobody affects my update value. That's the simple way of thinking about this property.
But can you explain why commutativity? Monotonicity is clear, but can you explain why commutativity means this? Just let's look in more details on the definition.
Because if you have to update sets of active cells, right? Because they're active, they have to change their state if updated, the A and B. Right? So they are ready to change. They are ready to change. And now by updating them together, we get the same thing as updating A first and then B. And obviously the fact that A updated doesn't change the values that B will update to.
But just before we go to this, let's look at this definition. It's not so obvious. So, for example, imagine we have A and B were active cells, and then we updated things in A altogether.
Yeah.
It's not obvious that states from B will remain active, no?
Yes, that's why commutativity requires that. So not all automata are commutative.
No, not all automata. No. But GB. So we do we require that B remains active or not?
Yes, we do, because if E doesn't remain active, then updating A and B together will have a different result than updating A and then updating B. because B are active.
Ah,
So they have to remain active. Otherwise, if they're not active and you update them, you get a discrepancy between updating all things together and sequentially.
and let me then ask you a more formal question. Imagine we have
Yes.
A and B, which are not just arbitrary sets. Imagine we make two updates. In
Yes.
some sets of cells, some of them active, some are not active.
Yes.
Then the same property remains true or not?
No. Because non-active cells can be activated by a neighbor which updated and activated itself. So this is so it's a much stronger property than commutativity, what you're talking about. Much stronger. If you do it for arbitrary sets.
So there is some kind of things, non-trivial things. So we do not say that we can update in any order.
This is not trivial, and the proofs that come are also not completely trivial. So yeah, we'll see more on that.
Okay.
So now we have a theorem which says that commutativity is the same as monotonicity plus invariant histories. Now, obviously, commutativity implies monotonicity. That's obvious. And now if we move to the next slide.
So just monotonicity was what? Say it again. Let's think about this.
Monotonicity was... Let's think about it as the other. Yeah. So if I can update, nobody can stop me from updating. That's monotonicity. And commutativity, if I can update, nobody can stop me from updating and nobody affects my update value. It's the easiest way to think about it. So now let's do the proof. So that monotonicity at invariant history implies commutativity is trivial because consider two active cells. Because it's monotonic, if one of them updates, then the other has to remain active. This is monotonicity. And it also has to update to the same cell as it would have updated if the other cell didn't update, because it has invariant histories. So essentially, monotonicity requires if we have neighboring active cells, one updates, the other needs to update, but it doesn't tell us to what. But invariant histories tells us to what, because it shouldn't matter in which order we update the cells, the history should stay the same. So that's the simple proof. Now the complicated proof. Yeah, here I wanted to, we'll still stay here. So that the commutativity implies monotonicity plus invariant histories. So actually here I wanted to draw something, but I'll have to do it without probably. So the idea is that we look at the synchronous update schedule. So it's update schedule where we update all cells at once. Right?
Ivan, I think you can write notes here just on this slide.
Yeah, let's see my laptop.
You can try to write in Zoom over the slides.
Yeah.
But while Ivan is writing, did you understand the proof of at least for the first time? Because I am lost. For me, it's too complicated.
No.
Anyone understood the proof of the first part?
Do you mean monotonicity
plus invariant history? Because for me, it's I cannot even grasp the definition all at the same time. It sounds very, but maybe someone can explain it again for me. Кто-нибудь понял это?
Нет, это невозможно было понять.
Окей, может нам невозможно, а умные люди, может, уже поняли. No, I guess Peter can explain, but maybe somebody else can.
Well, I mean, of course, this is for me also like 30 years ago.
Yeah,
so,
but still you have kind of unfair advantage.
No, I kind of remember that indeed from the two parts, one of them was not so trivial. So I suppose the second part was not completely trivial, but still So I think this is the theorem that probably already existed in various other.
Окей, но this is not a problem. The problem... Саша, Леша, может, вы поняли? Не?
Okay, I can try to draw.
Okay.
Now, I cannot draw because I don't have the rights. Can someone make a whiteboard? Who has the...
Let me try to draw.
No, there is a kind of pencil, but I try if you try to tap it, it doesn't work.
Yeah, it seems like you cannot create a whiteboard while someone is sharing the screen, so maybe we should turn it off for some time.
Okay.
But
I mean,
what should we turn off if we don't see the slides?
What are you trying to do?
No, Ivan, I think want to write something over the slides. And
no, but what is the goal? Goal is to understand the first proof, understand the second proof, or
So actually, we won't need these proofs. Like this is that much, right? It's about the result, about what exists.
Okay, maybe if we don't need this proof, it's indeed if even Peter can say it for sure now. Maybe we should move and see what maybe we can understand something else.
Yeah, this is actually the whole point of the talk, because as you can see, the characterization of commutativity and monotonicity is, although it's not too complicated, it's pretty complicated to understand, and also it's very non-intuitive.
And you have some better one. Let's go to the better one.
Yes, there's some better one. It has some flaws as well, but it's easy to understand.
Yeah, fantastic. Let's go there.
So let's move to the next slide.
Покажи нам следующий слайд, где будет лучше.
So this.
Дальше еще.
Да, следующий слайд. Ты пока то же самое показываешь.
Okay, so this slide is still about commutativity, but I'll just quickly say what it means. So we have seen that commutativity requires this property that updating any sets of cells in arbitrary order doesn't matter. And it turns out this is equivalent if we formulate commutativity for just singleton sets. So what this theorem says is if you have singleton sets of updates and they commute, so do all other cells. So do all other sets of updates, which is also not completely intuitive, but here is the proof. The idea is that cellular automata are local, so you can always look at a finite set of updates. And then from the finite set, you get the singletons, then you reorder the singletons, and then you order them back, and you get that reordering update sets doesn't matter.
Yeah,
so
it reminds something like this diamond convergence theory in lambda conversion or something like this. That whatever we do, it's not.
I think that's a less trivial theorem. Yeah.
Okay.
Yeah.
But if we don't understand even the more trivial one, then let's skip this also.
Yeah. So the idea behind this theorem is that commutativity is a complex property, but actually we can check it very easily because on the next slide, it turns out that we only have to look at local commutativity. So we have just to check if a single cell, if commutativity holds for pairs of active cells. And to check that it holds for pairs of active cells, we only have to look at the local rule function. And then we just have to check all the interleavings of local rule function with itself. So what happens if we update one cell in the local rule? Does it commute? What happens if we update the other cell in the local rule? Does it commute? So it turns out this property is actually easily verifiable algorithmically. You just take the local transition function and check whether it commutes with itself. If it does, then the global transition function commutes.
Mm-hmm.
And some examples of commutative functions are given here. So for example, the identity is clearly commutative. Then also the function which, let's say, it just adds 1 if it's smaller than the neighbors is also commutative. Because if you interleave, the updates don't change. And one of the more important theorems is actually we cannot do much better than commutativity, because deciding whether a cellular automaton has invariant histories it's undecidable. This theorem has a complicated proof, so you embed a Turing machine into very smartly. Actually, you embed a lot of them, and this way you prove that it's undecidable. So this was the algebraic characterization. So now let's move further. And let's talk about simulation, the topic that we have discussed before. So what does it mean for a synchronous cellular automaton to simulate a synchronous cellular automaton? So let's forget about asynchronicity for a second. Essentially what it means is that we can find some projection from our host cellular automaton, from its state, back, for example, k given states of a host CA, project them, and do n iterations of the cellular automaton, and then unpack the states again, and you get a bijection to the original automaton. So that was okay.
Wait a bit. So before you give the formal definition, so automaton B simulates probably n steps of B should simulate one step of A. Yeah.
Exactly. Yes.
And in the space direction, so we need each cell of B simulates one cell of A, or some rectangle in B simulates a rectangle in A. What you try to decide?
Some rectangle in B simulates one cell in A.
So it's single cell.
Yeah. So a rectangle of B simulates one cell of A, and then because B is infinite, you get infinitely many rectangles.
Okay. So for B we have some rectangle, and rectangle size is fixed, or what?
Yes, it's defined by this unpacking OM. So we can say it's an M by M square.
Yeah.
If we're talking in 2 dimensions, or in just an M by 1 rectangle if we're in 1 dimension. And essentially, so what we are encoding, the original configuration that we want to simulate into infinitely many of these rectangles, where each cell goes into a rectangle.
It's okay. Unpacking maps what to what? Say it again.
Unpacking maps this rectangle to a single cell. So it maps a cell from A to a rectangle in B.
No, it maps cell to rectangle, or a rectangle to cell.
It maps a cell to rectangle.
Cell to rectangle. So it defined on the cells on the states of A, and for each state of A we have some rectangle made out of states of B.
Yes.
And then then what we require. So what is tau? It's defined where and how it goes.
So the idea is that for B, to show that B simulates A, you need to find a large enough rectangle such that you can encode every cell of A.
Select some size of rectangle, yeah.
Yeah, so you need the size of rectangle M. Then you say, okay, B might take more than one step to simulate one step of A, so B is allowed to take n steps.
Yeah.
To perform one step of A, and also B is allowed to shift. So maybe instead of the same rectangle being at this exact position, maybe it shifted somewhere in space. And but the configuration is still the same, so we kind of allow shifting. So the rectangle doesn't have to stay at one spot; it may shift a bit if this is convenient.
But the shift should be the same shift for all the rectangles, so it's simultaneous.
Yes. So the whole configuration shifts. So you have a configuration of rectangles, and then after n steps, you get the same configuration, just encoding one step of A, which is potentially shifted to the right or to the left.
Yeah, but you mean just for every state of A, we have only one rectangle made of B states that corresponds to it, or we can have
No, it doesn't have to
several.
be unique. Yeah, we can have several.
So
It's a projection. So if we get a rectangle, we know exactly which state of A it corresponds to, but there can be multiple rectangles which encode the same state.
and there could be there are rectangles, but when we want to translate in one direction, we select one specific rectangle for each state of A, or we also can use any of them. When you say unpacking.
You can use, so you give me an encoded configuration and you encode it as it's convenient for you. But what I give you after that is a configuration that you can decode, and the decoding gives you one step of A.
No, just unpacking map. If it maps, if it maps only on each step,
It's subjective, but not in. It's injective, but
not subjective.
It's subjective,
but
not
still, there is another kind of mapping which, even if we have some rectangle which doesn't belong to the image of this O, we still can say which state of A it simulates or what.
Yes, so if it's a valid simulation and after n steps, what you get, you should be able to decode into a configuration.
And who makes the decoding?
You define it in advance. So you define it by this unpacking map O. So you start with O and you pack the states, then you perform n steps of the simulation. And when you are done, you look at these rectangles and say, this rectangle has to correspond to state.
Нет, все-таки я не понимаю, решительно не понимаю. Все-таки этот самый О, оно отображает состояние А в квадраты, или оно отображает квадраты в состояние?
Состояние в квадраты.
Состояние в квадраты. А
maybe
тогда
it's
как же...
better to call it encoding and decoding. Right?
Okay, but it's unpacking.
OM is encoding and
Okay, unpacking is encoding.
Yeah, but who plays then the role of decoding, or there is no?
So the decoder is done by the packing, so the O of -1 and a projection, because so when we have this rectangle.
But what is projection?
Окей, слушай, мне кажется, я понимаю.
Да, давайте.
Отдельным состоянием А соответствуют, как вы выражаетесь, квадраты, заполненные Б. И состояние Б.
Да.
Поэтому у нас имеются операции преобразования глобальной конфигурации в А в глобальную конфигурацию Б и наоборот. И вот эти два преобразования, туда и обратно, они определяются одним и тем же соответствием, вот которое здесь называется буквой О. Значит, в одну сторону это просто О, а в другую сторону О в -1.
Да. Нет, это бы я понял. Это значит, что когда мы применяем правило из B n раз, то получается то же самое, что если бы мы применили одно правило из А потом снова его закодировали. Ну и сдвинули еще.
Да.
Но вопрос в том, что в принципе может быть так, что в автомате B, помимо этой информации, которая вот соответствует декодированию, происходят какие-то внутренние процессы, которые нас не очень интересуют и которые обратно теряются.
Да.
Нет, что да, тогда или нет? Я не понял.
Да,
тогда, значит, тогда Андрей говорит, значит, тогда Андрей говорит не то, что вы хотите.
Тогда это не O to the -1, да, а decoding там может быть...
Should we use some different... We should be more specific here, really.
I mean, this is a known definition. So...
Okay, but do you explain this known definition? So Андрей, if I understand correctly, just
say... There will be an example after that. Maybe that will help.
Да, значит, из того, что здесь написано, и того, что Иван объяснил, Я так понял, что внутренняя жизнь автомата B, она через n шагов уже не видна. То есть вот в квадрате, кодирующем одну клетку автомата А, вот в этом квадрате, через
Да.
n шагов записано в точности описание нового состояния одной клетки автомата А и больше ничего другого.
Ну, со
Никакого
сдвигом, быть
мусора.
может.
Быть может, со сдвигом, да. Может быть, эта клетка в пространстве сдвинулась, но там в точности записан образ одной клетки А и никаких там дополнительных данных, никакого мусора от вычислений, вот ничего такого нет.
Ну да, вот мне
Андрей,
тоже
а вот что объясните. Значит, вот одна клетка заменяется на квадрат. Соседняя клетка на соседний квадрат. Они не перекрываются, эти два квадрата?
No, just the space is divided into squares, and these squares, if we look at after n steps and with some shift, they just behave exactly as A with unique encoding. So every element of A, as Andrei says, is encoded, but only one specific square. There are no other encoding of the same square. But I don't know whether it's correct understanding.
Yeah, that's how I understand it. Yeah.
Yeah, that's completely correct.
Then I don't
three
understand,
examples now.
understand at all that shift. What does it mean TV?
No,
Tau
it's
V.
happened. It's quite strange thing. But imagine that we have the simulation, but by some strange reason we get the answer. To read the answer, we need to shift the grid by some fixed vector. То есть вот we encoded our B configuration, made our A configuration, made n steps of B, and then we want to read the next configuration of A. We read it exactly with the same rules of reading, but shifted by some vector.
yes,
Not clear why it's needed, but okay.
It's like allowed for the simulation to be like gradually shifting uniformly.
Но на каждом шаге мы на один и тот же вектор всегда. Each step we move by one specific vector at the same, so we just move with constant speed, I guess. Our grid is moving.
Yeah, so the motivation behind this is to say we want to make the definition as flexible as possible, because if something simulates something else perfectly, but just shifts for some reason, it's still a valid simulation. It obviously does the same thing.
Okay.
It just shifts.
No, in fact, I disagree slightly. If you want to make it as flexible as possible, then I would put the shift to between O and O inversed. In the form as it is written here, it is assumed implicitly that the size of the shift V is a multiple of the size of a block, which encodes one cell of A.
Oh, this I didn't understand. Yeah.
So you for some reason you are not allowed to shift to some intermediate number of steps. This is a bit strange, but I think it's not a big deal. We can.
No, you can, because B doesn't have to be a multiple of A. B can be anything.
No, so we allow shift by a but not a multiple of M.
Yes. But let's move on to yes, we allow it, but we won't need it. So this is a very little detail that we really shouldn't be interested in.
Okay, let's try to understand at least something. Okay,
let's quickly there is a final definition on the previous slide. So this was the synchronous definition that we discussed. Now, our idea, we just take this definition, because there is no good definition for a synchronous case, and we just take this definition and replace the G with our invariant history. So they say that instead of having this global update function, we just now look at rows in the invariant history. So B simulates A, and asynchronous automaton B simulates a synchronous automaton A if nth row of invariant history of B with these shifts, backings that we just discussed corresponds to the evolution of A. Just a very natural extension.
Yeah,
Replace.
so we don't want to simulate asynchronous automata. A is synchronous.
Yes, we're simulating a synchronous automata with a asynchronous one.
But wait, Ivan. If we have asynchronous automaton, then we can also consider just normal evaluation.
Дай нам Бог разобраться с синхронным автоматом. Подожди, ты как-то это самое. So let A be synchronous, and then B can be asynchronous. But do we require to have to be commutative or invariant history or whatever?
We require B to have invariant histories.
We require to have invariant history, and we want this invariant history to be a correct implementation of A in this sense.
Yes, exactly. So it's again very natural.
Саш, подождите. Так что я хочу сказать, что если вот второй автомат B асинхронный, то это то же самое сказать, что он в обычном смысле симулирует, а кроме того у него вот есть эта история инвариантная. Это же разве не одно и то же?
Нет, потому что если в обычном смысле, потому что мы смотрим только на историю теперь, мы не смотрим на его эволюцию, мы смотрим только на историю. Мы ищем симуляцию в истории.
Совпадает с эволюцией.
Ну, там, в принципе, может быть так, что мы, когда состояния не меняются, мы это пропускаем, это момент времени. Поэтому, в принципе, если он синхронный, то, может быть, там эта история как-то иначе устроена.
Понял. Понял.
Maybe.
Okay. So, no, that's a completely valid point. So now let's move to an example. So this is the timer that was mentioned in the beginning. So there are two ways that were known how to make simulations of synchronous automata using asynchronous one. And the idea is very simple. So each cell stores a tuple, current state, previous state, and a timer. Now let's look only at the left picture at the moment. And so you have a timer, 1, 2, 3, and your state and your previous state. And the idea is very simple. As soon as you notice by looking at the timers of your neighbors that they are at the same timer or ahead of you, you can update. And if you're ahead of you, you use their previous state. And if they're on the same timer, you use their current state. So this is this. So here you have an example of an XOR on the left. So the first state is always the current state, and the second after the bar is the previous state. And as you can see, the next state is always the XOR. Each line is always the XOR of the previous one, the first value, and the second value is just the previous value copied. So kind of every cell again stores its own history of 2 cells and a timer to see how far ahead.
So the left picture is a synchronous picture or asynchronous one?
So this is an asynchronous picture, but every row corresponds to a synchronous evolution.
Yeah. So the general idea is that we just keep timer, and so we are okay. We are okay if our colleagues are in the same state, or even if they one state ahead, because they also remember their previous state, and we know that we are one step ahead and can use the previous state.
Exactly. And if they're ahead of us, we just if they're behind of us, we just wait for them to catch up. And only
we cannot go forward because we will be too fast. And then our neighbors will not be able to use our state because we lose our old state.
Exactly. So this requires 3q² states because the timer is free states to know if someone is behind you, same level, or ahead of you. And obviously you save your state and the previous state. So this is the famous free timer construction. Now you can improve it a bit by slowing it down, and instead of saving a tuple state, and now we can look at the right. Instead of saving the tuple state in every cell, you actually save like begin, then the tuple state, and then the end. And it works exactly the same way. just that you only update, you take 3 time steps to update yourself.
No, can anyone explain what are the B and how they work? Just repeat the explanation for me slowly. В чем состоит план самый вот справа? Значит, с таймера я примерно понял, что если бы вообще мы могли бы, так сказать, не заботиться о состоянии и хранить просто состояние во все моменты времени.
Чему равно Q вообще в этом примере?
Q это число состояний, я так понимаю.
Да?
Да, число состояния автомата, которое мы симулируем.
Да.
Q равно 2, а 3Q квадрат равно 12. Где здесь 12? Я что-то не понял.
12 это 4 four cases 0, 0, 0, 1, 1, 0 and 0, 1, current state and the previous state, and one of the 3 cases of timer 0, 1 and 3.
Правильно я понял, что нужно 12 шагов, чтобы один шаг?
Нет, шаг по-прежнему один, не нужно их 12 шагов.
А так что значит 3Q квадрат real-time simulation? What does it
Это
mean?
число состояний, the number of states is 3 square. Because each cell has a timer modulo 3 and current state and previous state. So we had 3Q square. That I think I understand.
And one step will be simulated by one step.
And one step is simulated by one step.
So yeah, can you explain again the other the second possibility, the Q square plus 2Q?
Yeah. What is happening with B, E, and Q square plus 2Q?
So now the idea is now that we use 3 steps to simulate one step. And the idea is that we start in a step where the configuration is encoded and we just have the B to indicate that we're beginning. Mm-hmm. And then each of the B's, each of the cells in this configuration, it updates into a pair state where it again stores its state and the previous state. Mm-hmm. But instead of next time when he is in a pair state, updating to a pair state again, it updates to a 1E state, where the end state is. So essentially, we have 3 steps. Start with a configuration, form a tuple configuration, and then discard the old state. So again, to repeat, we start with a single row, then we have a row which tells new state, old state, and then the third row is just the new state. So we're slowing down the simulation.
So the timer is still the clock is still modulo 3, just named differently.
The clock is now the clock. Yeah, exactly. So it's still a modulo 3 clock, but now it takes the whole loop of a modulo 3 clock to make one step of a simulation.
So initially, all states have clock 1, clock B.
Exactly.
And then what they do on the first step, they perform
an update and store their old state.
And store the old state.
Yes, and now when they're ready to update again, because all of their neighbors caught up with them, they discard the old state and only leave the new state.
So they see that all the neighbors already performed the computation.
So so you recognize that the neighbors caught up with you in that the neighbors have the symbol B?
No, don't have any more symbol B, I guess.
Exactly.
What do you mean?
So you can interpret.
No, you see, if your neighbor still have B, it means that it's not already ready. So you should wait and not finish your step. And if your neighbors are already ready and don't need your step anymore, your state anymore, you can forget your old state because they will never ask about it. That's, I guess, the idea.
Exactly.
So neighbors have to be in. Your neighbors would have to be in state E. No. So when can you update?
If all the neighbors are in state B.
If all the neighbors are in state B, yeah.
No, just you perform the real computation if
Yeah.
you and your neighbors are in state B,
Uh-huh.
and then you keep
Or your
your
neighbors
old,
already perform
then you keep your old state until you see that all the neighbors already made the computation, and so they don't need your old state anymore. If you see this, you move to timer E. And then if you see that you are in timer E and your neighbors are in time E, you switch them to B.
and start the whole thing
And
again.
start the whole thing again. But why do we need, why cannot we join B and E? Зачем нам отдельно B и E? Почему нельзя было бы их объединить? Наверное, есть
Because then
какая-то...
if you are in a double state, then if you see a B, you wouldn't know is this the B behind you or the B ahead of you. So you need the E to know this guy.
Maybe your neighbor is ahead, or maybe he is behind.
Exactly.
Any constant 3 or greater would work, it seems.
Чего?
Мне кажется, любая константа, которая больше 2, сработает.
В смысле, что можно было бы еще сделать?
Ну да.
Мы экономим тут все наоборот. Мы хотим... So we don't need... We need q square without E and B, and 2q with one q for E and q for B. So we have small economy here. Okay.
Okay, so this is the old construction. So now let's see how we're doing in our search. Can we characterize all automata with invariant histories? Well, we can use commutativity, but it doesn't characterize all of them, just some of them, and it's hard to interpret, as we have all seen. Then we cannot decide if an automaton has invariant history. This was the small theorem. And then we can also construct arbitrary complex automata with invariant histories by using this timer that we've just seen before, because the timer obviously has invariant histories. Doesn't matter what you do, you always get these clean rows of updates. And one of the questions that we haven't tackled yet is what are the limits of asynchronous computation?
Yeah. So what do we care really? So there are two problems. First, that we need more states, and second problem, it's not clear how fast everything will go, because maybe something is not updated, and it will make people wait until it becomes updated, or this is not the problem we are trying to deal with.
This is not the problem. This is not the problem. Another problem is that we need to see both of our neighbors to make the simulation technique before. If you just see the one neighbor, this doesn't work, for example.
Yeah, but
right?
Okay, but what is the problem? Why don't we see another neighbor?
No, if we define the neighborhood to just see the neighbor to the left.
If you just for one directional automata, it doesn't work. That's what you are saying.
Yes.
Excuse me, I also wanted to make a remark. No, maybe it should have said earlier, right? If it is about minimizing states. So the paper by Berman and Simon uses a different mechanism. Somehow cells communicate with neighbors, whether they are ready or not. I don't, so one should check it out whether it is actually, it has more states or fewer states. It's not, the correspondence is not completely obvious. So it's not.
But maybe Peter, maybe you can also say another thing. So imagine, so this updates happens, I don't know, with some probability at each step. How do you, can you say informally how big will be the delay? So if we update every step cell with probability 1/2, then it makes our computation how slower it becomes.
A constant factor. Constant factor. That's what Berman and Simon showed.
Constant factor.
On the average.
Yeah, for their construction or for timer construction?
Both, I think.
For both, yeah.
Okay. But that's a different route. We're not looking at randomized. We're really looking at worst case scenarios. So we don't care how much slower it is as long as it works. So now let's move to the new results.
Yeah.
And so now we actually see, now we introduce a very simple concept, which is called flip automata networks. So there's a concept of automata networks, which are just cellular automata, but instead of grids, you have arbitrary graphs. and then every node in the graph can have its own update function. So it's a really crude generalization. And what we define is flip automata networks. It's like automata networks, but you have directed transition between the nodes. And now the idea is that the node can update only if all of its neighbors point to it.
No, first of all, too fast. So we have a finite graph or infinite graph?
Infinite.
Infinite graph. And each vertex has an edge, can have, they are connected by directed edges.
Yes.
And this means what? They read
yes.
according to edges, or they send their influence according to edges.
So if
the transition, you need to know the states. If you want to make a transition in vertex A, you need.
There isn't an example which will exactly explain this question.
But just say that yes or one bit. You just use states of the cells with outgoing edge or incoming edges.
Incoming edges to read.
Yeah, so you read incoming edges.
Yes. So this one, which is in the center, can update.
What you mean flip edges? States are in edges or are in cells?
States are in cells, but we can also flip the edges.
And what does it mean, flip the edge?
So let's go to the next slide.
Okay.
So you see what just happened. A cell in the middle, it looked at all of its neighbors, updated its state, and flipped the arrows.
It changed the direction of the arrow changes.
Exactly. And now you see different nodes are active because now all edges in the corner nodes are pointing. So now they can update because they got all the information. And now if we go to the next slide, they updated, and now these ones are active. So it's a modification, a very simple one, but we claim that actually it also has invariant histories. Oops, and it's very easy to see why, because now we only care about our neighbors. And kind of intuitively, because we probably don't want to get a formal proof, intuitively, I wait for all my neighbors to be ready, and as soon as they're ready, I update. So I don't care what happens around me, because I update only when I have full information about my neighbors. So as soon as my neighbors are ready, I'm update, and in what order they get ready is not important for me.
But so you wait until, so when you perform an update, you just wait until all the edges, all the edges are oriented to you, or what?
Exactly.
Well, I think this is actually, I think this is something like the Berman-Simon construction.
Yes,
they have indeed something like this, so kind of edges act like buffers, and yeah.
But for example, here we have two incoming edges and two outgoing edges. So does it mean that we cannot make update, or what?
We cannot make an update. 2 is stuck, 2 has to wait. The center cell has to wait until all the edges are incoming. You're stuck if you don't have all the edges.
It's possible that all vertices are stuck. Because
yes, it is possible.
Yeah.
So now okay, this is a completely different thing than cellular automata. So the question is, how can we use it? And the idea is very simple. So if we move to the next slide, we actually define arrows between neighboring states. So let's say we have a binary cellular automaton. If the neighboring states are in cell 1 and 1, then we add an imaginary arrow to the left. The same for 0, 0. But if it's 1, 0, 0, 1, we add the arrow to the right. This way, the configuration, which is here, the 1, 0, 0, 1, 1, 0, 0, 1, 1, automatically induces these arrows. And now if we update this thing like we would, it also updates the arrows.
No, I am
So this is
completely
a
lost. What is... Кто-нибудь понял, что вообще за стрелочки, куда они...
Yeah, so
зачем?
yeah, but what he's doing, I think he's simulating this arrow thing with additional states. But he doesn't need 3 states for that, only 2.
So we simulate error, this new type of automata using old type or what?
Yeah, I think.
This is a cellular
Yes,
automaton.
yes. So instead of these flipping arrows, now you have just 2 states, right? 1 and 0, 2 extra states, 1 and 0.
Yeah.
And then with that you can simulate the arrows the way he shows, right? I mean, that's my understanding.
So if they are the same, the arrow goes to the left.
Yes.
And if they are different,
then it goes to the right. And if all of the arrows point to me, I just flip my state from 1 to 0, from 0 to 1.
But these states are additional states which change in parallel to the computation, or what?
We just look, we're not simulating anything yet. We're just look at the binary cellular automaton with state 0 and 1, and add imaginary, just imagine that there are arrows in between. And force the cellular automaton to update only when the arrows are pointing to it. So actually this thing corresponds to rule 212.
So we have some fixed rule from Wolfram class,
212,
and we make it asynchronous by deciding that we want to behave if only all errors are incoming.
You don't even have to make it asynchronous. So it's just a local rule is defined that we only make that you only change your state when the arrows point to you. It can also be synchronous.
Yeah. So essentially, instead of using modulo 3 clock, you can say that use a modulo 2 clock, but it is in a different way, right? So instead of using 3 extra states, use only 2 extra states and use this construction.
Yes. But this is not the complete construction, obviously, because at the moment this just doesn't do anything yet.
Yeah.
So let's move further.
Okay, let's move, and maybe later someone will explain what is happening. Okay.
So actually, now we can visualize it even better. So now if you think as a right arrow as a slope, as a diagonal slope, and a left arrow as the opposite diagonal slope, you can visualize this whole arrow configuration as a mountain valley landscape. And now the evolution of a cellular automata, the asynchronous one, corresponds to, like, you can think of it as a wave slowly filling the space-time.
Oh, so it's one-dimensional construction.
Yeah, so at the moment this is all one-dimensional.
Yeah.
So now we can visualize these arrows using slopes, and then the slopes, as you can see, naturally encodes the space-time. And you can see which cells are ahead and which cells are behind by looking at their slopes.
Yeah. Okay, so intuitively there is some idea is clear, but okay, let's see. Let's continue and see how you use it.
So now there's actually a theorem that any von Neumann in any dimension, not just 2-dimensional, 1-dimensional, any d-dimensional setting, where no 2 neighboring cells can be active at the same time. So this is our constraint. It's a bit weaker than commutativity. It's a bit stronger than commutativity. It embeds flip automata network. So again, maybe proof is not necessary because, we're a bit low. But the idea is essentially that if you take any asynchronous cellular automaton with von Neumann neighborhood, such that no neighboring cells can be active at the same time, you can rewrite it as a flip automata network as we have seen it before.
Okay, von Neumann is just we have neighbors in one coordinate,
Von Neumann means it's a cross.
4 neighbors for 2 dimensions, yeah.
or in 8 or 6 neighbors for 3 dimensions.
Yeah.
So this is another way of characterizing such ACAs with invariant histories. So now instead of thinking of commutativity and monotonicity, you can just flip. You can just think of it. Okay, actually these ACAs, they have like invisible arrows, and they only update when all the arrows point to them.
Okay.
And this is true for all von Neumann ACAs which satisfy this condition, which is a bit weaker, a bit stronger than commutativity.
Okay. Let's assume that we understand something. Okay.
So now if we move further, we can actually simulate any von Neumann or Moore ACA using this technique. And now the theorem says that instead of q squared plus 2q, which was the previous best result, we just need 4q states. And the idea is that you embed these flip automata networks into cellular automata to simulate the synchronous cellular automata. So essentially, it works like a synchronous cellular automaton simulates a flipped network, and a flipped network simulates a synchronous cellular automaton.
No, but we simulate it in the space. We simulate cell by cell or a square of some size.
So now we have a square of 2 by 2.
So we have a square of 2 by 2.
Yes, so one E cell and 3 O cells simulate one cell of the underlying automaton. And how the construction works, very briefly, again, think of it as mountains and valleys, or like arrows for that reason. So the O cells, they compute the XORs of the E cells, and then the E cells perform the local transition.
Okay, so there is some specific construction. Probably we cannot understand it now, but at least we get some idea. So if you allow make the size in space twice bigger, then we just instead of 3q square state can use 4q.
Exactly.
I don't think you need to make the size of space bigger. It's just that somehow you require. You will move. You can imagine it that you always move like 2 steps at a time. So always so everybody has to it is divided into even and odd neighbors, and somehow so your even cells has odd neighbors, the odd cells have even neighbors, and then you have to. You can move only when all your neighbors are ahead, but then you move 2 steps and you will be ahead of all your neighbors.
But how can you move 2 steps if you don't know your?
Well, I mean, it's not too. I mean, just measure the time.
The time increases by 2.
You measure the time in terms of. I mean, the even neighbors move always to even time steps, and the odd neighbors go always to odd time steps.
Exactly. So this is like mountain valley. If you think about it, you were a valley and you become a mountain. If you look at the previous picture, and so essentially you can never be at the same time with your neighbors. You're always either 1 step ahead of your neighbor or 1 step behind.
So you decrease the space density or not?
The space density is decreased because now we need more, because 1 E and 1 O together.
So you use 4 states to simulate 4 cells to simulate 1, or you use 1 cell.
Exactly.
You simulate 1. You use 1 cell to stimulate 1, but you use special arrangement.
Maybe he can use it, but it doesn't. He doesn't. I don't know.
Yes. So we're using multiple cells. So actually, the E cells, they carry the real value, and the O cells are just helpers.
Yeah, so in this construction, at least the space density becomes 4 times less, and so somehow it's not much. If you want to really compute something, we should just take 4q states, but then take the 4th power of it. So it's kind in this sense.
Yeah.
In terms
I mean,
of
from
bit,
a practical,
we don't get improvement, but okay. Yeah.
from a speed we don't, but like we get less states, and this is what we care about. This is
Less
our
states
optimization.
locally, but more states in general because density
Yeah, but
is
it's
smaller.
infinite anyways. It's because it's the infinite grid
Okay.
anyways.
Okay.
Don't care.
Okay.
So actually, we can further improve this if we just do it in one dimension. So this is the next slide. We can improve it even further, but this is more tricky construction where you don't just flip, but you also shift. And I don't think we need to go into the details because
but
it's
in
even
this
more
case,
confusing.
you use one cell to simulate one or two.
Two cells.
Two cells. Yeah.
Yes.
Yeah.
But we get it down to 3q, which is so now we have a tertiary timer. So essentially from 3q squared we go to 3q, but at the cost of using two cells, which is not really a cost because it's infinite.
Okay.
Okay, but now this
Is it
this was like sorry?
Is it possible to stay at the same number of states?
Number of cells, you mean, or number of
Number of
states?
states. Like, for example,
So
our
just
automaton. For example, our automaton it used for just 2 alphabet symbols states, and then our construction it made it to use like 8 states or something like this. Can we reduce it back to 2?
No, I don't think it's possible. What are we doing? What is happening?
Probably Kolya wants to know how much slides remains because we are 10 minutes out of schedule.
Okay.
Yeah. So, but maybe indeed we should make a break now, and maybe someone can I don't know, Kolya or Lyosha, maybe they can look at the slides and try to understand things in advance to be able to comment online because it seems that it's necessary. Может мы тогда продолжим в следующий раз, но и кто-нибудь еще заранее посмотрит, чтобы как-то разъяснять для дураков вроде меня, что происходит.
Прошу прощения, есть текст, который можно посмотреть?
Вроде там есть был в аннотации даже был текст.
А можете прислать ссылочки на текст или презентацию в письме с записью?
Там были приложены.
Окей. Я пришлю тоже. Хорошо, я пришлю. Значит, sorry, we indeed we usually we try to finish at 6, but it's now 10 minutes behind, and maybe someone can kind of go over all this and make some kind of short explanation for dummies what is happening and what we try to achieve and so on.
Yeah,
Okay.
I mean it's nothing really complicated.
It's just I think I'm just bad in understanding what you want to say, and you are bad at explaining to dummies. So this is problem. Okay. Okay, so maybe I don't know what about the next time, Andrei. Maybe you will explain about this dividing complexity by 2 problem and your example.
What divided by 2?
Ну, что нельзя найти араху, который уменьшает сложность всех слов в 2 раза. Ну, то, что вы мне рассказывали, что вот это вытекает из каких-то результатов о чем-то. So there is a general problem. Imagine we have 3 strings, A, B, and C. They have some complexity. And conjecture, it's always possible to find some oracle which decreases all the complexities, making them twice smaller. And now it seems that Andrei has a negative answer for this conjecture.
Да, наверное, я это могу рассказать. I think I can explain it, especially because it's not me. It's
Even better.
Just we need to read the the appropriate line in the paper by Tao, Bourgain, and Katz, or some people following this line of research. So some mathematicians somehow answered our Sasha's question without
Even knowing.
being aware, without knowing it. Yes, exactly.
Yeah. So I guess it's just for actually what is funny that for two strings it's always possible. If we have two strings A and B, we can always find an oracle which makes them twice more simple. And it's a general statement. And
But
it was
what is the difference between two strings and one string here? I mean, you can combine two strings into one somehow. Oh, so I mean,
I think Sasha is frozen. We want to add an oracle such that with respect to this oracle, both complexities, or in other case, all three complexities are reduced by 2. And the strings can be correlated. They have they may have a mutual information.
So if you combine the two strings, maybe you can decrease the complexity by half, but then it's the complexity of the combined strings. It's not clear that both of them.
Yeah, exactly, right.
Yeah. Interesting.
Should it be clear or not that for two strings it is always possible?
Это на самом деле очень забавное топологическое рассуждение, оно тривиально. Пусть у нас есть две строки А и Б, и мы возьмем в качестве оракула там 5К битов в строке А и L битов в строке Б. И так самым для каждой пары К и L мы получаем некоторые значения сложности относительно этого нового оракула. И получаем точку. We get a point on the plane which depends on the other point of the plane. How much bits we take from A and from B, and what are the complexities. And if we look how this point moves, we see that it goes around our point which we want. And since it's continuous, for topological reasons, we cannot avoid the point inside the trajectory.
Oh.
We can start with this nice argument next time. Andrei, I hope, will explain it. It was in some old paper of his, and so he can start with explaining this.
Yeah.
I guess it's a very funny argument because we use topology to prove something about Kolmogorov complexity.
Yeah, that's interesting.
Yeah, and still, even we have some translation in a game. So we use topology to prove that some game has a winning strategy. So it's looking a bit ridiculous, but still. Okay, so let's decide that we will do this, and then maybe someone like Lyosha or Kolya will look at the paper, and then we will be ready for maybe in 2 weeks for the continuation of today's talk. Okay? Yeah. Yeah. So I also Laurent, our colleague who was also in the seminar, Laurent Benvenu, make an HDR, что соответствует докторской диссертации Habilitation dirigée de recherche.
Oh.
And I was there, and I made almost full recording, video recording, and I put it in the seminar channel in YouTube, and I will also send and he explains several very interesting results, and maybe we should ask him to provide a kind of series of talks about these results, because I didn't follow his new work.
Yeah, of course, interactive would be more interesting.
Yeah, of course. No, but no, it's just a kind of a menu. We can choose something, and then we can request him to provide a talk explaining this or that. Yeah. No, there was no proof, nothing. Just a short explanation No, like it was 1 hour explaining his work for 10 years or something like this. So it's just like this. Okay, so next time Andrei, yeah?
Okay.
Okay. Yeah,
Thank
so
you.
Andrei seems to be here, so he seems to agree with this plan.
Okay. Yeah.
Okay. Okay, thanks for our today's speakers, and we hope to get some more understanding later.
Thank
Yeah,
you.
I should have made it shorter, I realize, and
Нет, но на
make
самом
it
деле как-то
sentence.
объяснять по-простому принятых понятиям нижних чинов, как-то вот это было бы здорово.
Ну,
Ладно.
просто, понимаете, я столько работал с этим, что так привык, что мне кажется, все очевидно, хотя вначале я сам ничего не понимал, поэтому я сейчас уже забыл, как я все не понимал.
Нет.
И
А вы когда-нибудь преподавали каким-нибудь идиотам? Это был бы очень полезный такой опыт, потому
я
что...
вообще-то, да, я 4 года вел семинар.
Да. И что, они что-то поняли или как?
Но там же я простые вещи преподаю, то есть как
Ну
бы
вот,
там
не
всё.
знаю. По-моему, это самое. Ладно, поживем, увидим. Окей. And Bruno Bauens will send a note from the note for his previous talk. He still keeps changing, and he promised to send it later. Okay.
Okay,
Thank
bye.
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 Before the
Thank you.
talk, it's interesting.
Yeah, please
Thank you.
send. Yeah, Kolya. He left. I just to make sure I will get a notification about the next time, because I'm not sure I'm.
You are okay. I will add you. I thought I added you, but
Because
let me check.
I did get notification about this, but I think it was personally by Kolya. So I mean.
Okay. No, if you don't mind, I will add you to the list.
Thank you. If I'm not on the list, please.
Yeah, it's strange because if then you should get the notification. But okay, I'll check.
Yeah. Thank you.
Хорошо.
Bye.
Спасибо.
Спасибо.
Пока.
Thank you. Interesting talk.
Yeah. Ладно.